So this topic is on building number sense. So we should start with the first question, and that is, what is number sense? Number sense is the ability to work with, understand, and communicate in the language of the quadrivium. Arithmetic, geometry, music, and astronomy. Or numbers, numbers in space, numbers in time, numbers in space and time. So how do we build number sense as classical educators? Number talks are a great way to do this. Number talks are short teacher and class discussions about numbers designed to build number sense. As classical educators, these talks are structured using a question-answer, Socratic method dialogue approach, and they enter our classroom in two ways. Either intentionally, design time, these are usually 3 to 5 minute number talks, within the lesson plan directly related to the concept or topic being studied, or what I like to call an impromptu talk, typically 1 to 3 minutes, because of a student question or comment about the topic being studied. Both types of talks will be aided immensely with regular memorization of math facts, math formulas, and math terminology. In this way, we differ from progressive and constructivist models which demonize memorization, claiming it is not real learning or real knowledge. The last thing to keep in mind is that you will build number sense best in your students if you know what is still to come down the quadrivium road. So today, when I start to cover concepts that are above the grade level that you teach, these concepts you should still investigate as a teacher because they will equip you to direct your number talks for younger students in the direction of mathematical thinking that they will need in the future. For the remainder of our time today, I will provide some examples for topics for number talks. My goal is to get to as many of these examples as possible. So in most cases, I'm not going to lead you through a number talk as if you were students and I was a teacher, but rather I'm going to highlight how you can create a number talk from them. And I will follow the outline that you have in front of you. So let's start with number talks about fundamental operations. Let's do addition and subtraction first. The definition of subtraction is adding a number's opposite. So x minus y is the same as x plus negative y. Because of this, number talks that focus about addition and subtraction are greatly aided by use of the number line. So let's start with the number line and talk about that. It's always important when you introduce number line work to your students to start at 0, not at the number. So if we did the problem 2 plus 3, for example, you wouldn't want to start your students at 2 and then have them move 3 to the right. Instead, you'd have them start at 0. They would move 2 to the right, followed by 3 more to the right. Then, looking at the 4 other options with those two numbers, 2 and 3, if we did 2 minus 3, they would start at 0, move 2 to the right, followed by 3 to the left to get to -1. If they did -2 plus 3, they would start at 0, move 2 to the left, and then 3 to the right to get to +1. And if you did -2 minus 3, you would start at 0 and move 2 to the left, followed by 3 more to the left. Students in this way then start to see that adding two positive numbers or taking a negative number and subtracting another one is actually the same answer, but just in opposite directions of the number line, thus building number sense. I also, one of the kind of chants that we do in my class is I teach my students that the sign in front of the term goes with the term. So you could then commute all 4 of the problems that I gave you and have them do those again. The next thing I want to introduce to you is some subtraction methods throughout the world. For all of these problems, I'm going to use the subtraction problem 783 minus 298 for all of our problems. Now, for all of these methods, number talks should discuss with your students why the algorithm works and what is going on with the process. All of these methods also help to build in your students an understanding of base 10, which is the system that our number is based on. So the first method I want to show you is the reverse method. This is an ancient algorithm from India. You're actually going to begin at the left side of the problem for this one. And because 7 is larger than 2, you can do 7 minus 2, which is 5. And then when you get to 8 minus 9, you recognize you can't do that. So we're going to actually borrow here from the 5, and it becomes 4. And you carry the 1, and then 18 minus 9 is 9. Again, 3 minus 8, you can't do that. And so you'll borrow here from the 9, it becomes 8. And then 13 minus 8 is 5. And because that's the last one, you just kind of put it with the rest of your number, and the answer is 485. The second method is the Treviso method. This comes from Europe. It's a European algorithm. On this one, again, the numbers are written kind of in the way that we would write it. This algorithm starts at the right-hand side, which is what we do in America. But instead of borrowing over at the beginning, what the Treviso method does is it asks you, how much from this bottom number do we have to go up, if you will, to get to 10, because we're in a base 10 system? The answer is 2. And so you add 2 to both the 8 and the 3, and then you write this number down. Now, because you borrowed, you're going to change that to a 7, and then you're going to do the same thing again. Because 7 is smaller than 9, you asked, what can I do to add to get to 10 for that bottom number, which is 1 in this case, and you add the same 1 to the top, and 7 plus 1 is 8. For this last one, we did borrow, so we have to change that to a 6, but then 6 minus 2 we could do, which again is 4. So that is the Treviso method. And again, as I'm showing you all of these, I think students are just going to be fascinated to see different ways that you can subtract, and asking them, why does this work, especially if you have older students? Why does this method give us the same answers? This method gives us the same answer as the way that we've learned how to subtract. The third one is called the break apart method. This one is really good at helping students see numbers in expanded notation. So for this one, we'll write it going horizontally. But 783 minus 298 is the same as 783 minus 200 minus 90 minus 8 in expanded form. And 783 minus 200 is 583. We then look, because this is a 2-digit number, that 83, okay, we want to do 83 minus 90. It would be easier to write 90 as minus 80 minus 10. It's the same as minus 90. And then when we do 583 minus 80, we get 503. Here, most students can subtract 10 pretty easily. So we get 493. But then instead of doing 3 minus 8, and again having to deal with borrowing or negative numbers and so forth, we could change it to, 3 minus 5. Because minus 8 is the same as minus 3 minus 5. So you're teaching students to break apart the numbers into their expanded form that allows them to subtract more easily. Now this one takes up more paper. I'm going to show you a method in a little bit that takes up very little paper at all, and students love that. They love not showing. I mean, it's not about not showing their work. I think they're just all like, you know what? We just want to conserve this paper. A lot of this paper. Just don't want to use it. Okay, so that is the break apart method. The next method is called the compensate method. So in this one, we're trying to find compatible numbers, actually through addition this time before we subtract. So in this case, if you notice that when we add 2 to both numbers, because 298 is really close to a very easy number to work with, we get 785 minus 300, which again then, without any borrowing at all, is 485. Right. Okay, the next one is called the subtract in place method. This is one of my favorite methods because it has students working with negative numbers, which again goes back to what I said before about using the number line and helping students understand the opposite sides of the number line. So for this one, 783 minus 298, we're actually going to just subtract left to right, just the way that we rate. So 7 minus 2 we can do, and that's 5. 8 minus 9 is -1, and 3 minus 8 is -5. So like we did with the expanded method, right, before the break apart method, notice we're saying we have 5 hundredths, a -10, right, because it's 1 in the 10 spot, and a -5 more. So this is really 500 minus 10 minus 5, which is 485. Okay, so again, these algorithms give them different ways to think about addition and subtraction, work their understanding of our base 10 system, and also work both sides of the number line.
What's the name of that?
This one was called the subtract in each place method. Honestly, I just came up with that because online it doesn't really have a name for it that I found, so I just said subtract each place.
And the one before that?
The one before that was called the break apart method. It is actually online called the break apart method. And then before that was the compensate. Compensate, break apart, Treviso, and then the reverse method. Yeah. All right, let's move into multiplication and division, topics that you can talk about with those two operations. Just like subtraction is adding a number's opposite, so dividing is multiplying by a number's reciprocal. So x divided by y is the same as x times 1 over y. So number talks focusing on multiplication and division will include a lot of discussion about fractions. Remember what multiplying is. Multiplying is just fast addition. It's just adding in groups instead of adding in single units. So skip counting and, of course, knowing your multiples, along with the memorization of multiplication tables, provide a solid foundation upon which to build number sense. I hope that those of you who are teaching the very, very lowest grades that we have are going to hear throughout my presentation that we need these kids as they come through. We need them to have their facts down. We need them to memorize them. And it is okay that they don't understand all the whys and that they can't explain the algorithm in first grade. Okay, we don't need them to explain it. We just need to have those things down so that when we do work with these, they have that kind of understanding of patterns and counting and adding in groups and so forth. Okay, so the double half method is what I want to show you next. This is a great mental math exercise. You should do this out loud and orally, and this is one I am going to kind of show you as a number talk. Now, typically I would only do 1 or 2 of them. I'm going to give you 3 examples here just so you kind of get the idea. You may have to model these at first with your students, especially as you are introducing it. You're going to want to model especially what they should say. Okay? Because what they're saying is what they're thinking. And when they do mental math, you want to be able to have, as a teacher, a way to evaluate what's going on up here. Okay? Because if they're doing it mentally, we don't actually know unless they're saying it out loud. So here's an example for this one. Let's see. So all of these are mentally evaluated. Okay, so we're going to mentally evaluate the problem 3 times 18. So a student would stand up and a student would say, 3 times 18 is the same as 6 times 9, double half. And have them say the words double half, because that's what they did. And 6 times 9 is 54, because they have the fact memorized. Okay, here's another one. 6 times 14. Student would stand up and say, 6 times 14 is the same as 12 times 7, double half, which is 84. For older students, you can also do this with algebra. So suppose you have mentally evaluate 5x to the 4th if x equals 2. So a student would stand up and say, 5x to the 4th is the same as 5 times 2 to the 4th, which is the same as 5 times 16, which is the same as 10 times 8, double half, which is 80. Okay? So having them kind of work through that process out loud helps to build number sense, and also helps you as a teacher evaluate that they know what they're doing mentally with the numbers. This is also a great exercise when you adjust numbers in scientific notation, when the mantissa is 1 or more powers of 10 too large or too small. So if you have 15 times 10 to the 4th, the student can say this is the same as 1.5, we're making it 1 power of 10 smaller, times 10 to the 5th, 1 power of 10 bigger.
Yeah.
So with all of these problems, we are multiplying and dividing by 2. When we work with scientific notation, we're multiplying and dividing by 10. All right, next is dividing by a fraction. So many of us, especially if you get into the upper elementary and middle school years, we teach our students kind of the algorithm. Dividing by a fraction is the same as multiplying by its reciprocal. Okay. Now, and students know this and they know how to do it. In other words, they know how to crunch the algorithm. But we need to make sure that as we're doing these number talks, we sprinkle in the Lutheran question. What does this mean? Okay. Now, dividing by fractions, just kind of is very interesting because students are like, why is our answer always getting bigger when we're dividing? Shouldn't it get smaller? So this is a great number talk to help them understand what does this mean. So let's take the example of 6 divided by 3/4. What I have students do in my number talk is I have them draw 6 circles. Okay, if it's really close to lunch, don't call them pies or donuts or anything like that. Pizza. Just 6 circles, all right? And because we're dividing by fourths, in this case 3/4, we're going to take each of our 6 circles and we're going to divide them into fourths. Dividing by 3/4 means we are taking groups of 3/4 and we're trying to see how many groups of 3/4 we can make out of 6. So there's my first group. There's my second group. There's my third group. There's my fourth group. There's my fifth. There's my sixth. There's my seventh. And there's my 8th group of 3/4. So there are 8 groups that we can make 3/4 at a time out of the number 6. So this is a great way for students to kind of visually and also that they can do this verbally explain what's going on when we do 6 divided by 3/4. And you can get more complicated than that if you want to down the road. Okay, moving on. Division, distribution, and fractional coefficients. Let's take this problem. This is definitely for older students, middle school, early high school. Suppose you have an equation in standard form, and you ask the students to write this in slope-intercept form. Well, they should know that we have to isolate y, right? Y equals mx plus b. So the first thing they'll do is they'll move the 2x over to the other side. And if you've worked with them well, that the sign in front of the term goes with the term, they won't forget that negative sign. They know that the 2x, also negative, needs to go in front because y equals mx plus b. We want the x term to go first. And here's where they may get a little bit, maybe not confused, but they just need some help on how to show it. They know what to do. They have to divide by -3. But then how do you make it look like in slope-intercept form? So many may write it like this. And so you could do a number talk talking about how this, you could even do this one in front of them and ask them, is that the same thing as this? And they should say, yes, that makes sense. You just divided each term by -3. Okay, so what property did we use? So getting the opportunity to have it back and forth to help them not just memorize the properties, okay, but this is how we apply it. This is distribution of division. They're really good about distribution of multiplication, but then with division, they just don't see it as often. So this is a good reason to talk about distribution of division. Then, of course, the negative signs cancel out. And then the last thing I would do is I would say, you have it now written like this. Is there a better way that we could get that to look more like slope-intercept form? So here's where you can talk about pulling out something in the numerator and denominator as a fractional coefficient. Okay, so that you really see slope, you can see m. All right, let's talk about the remainder. This is one of my favorite talks. All right, so let's do 11 divided by 2. And I want you to write this as a quotient using the remainder system, R period, okay? So students would do this, 2 into 11, and they would get 5 remainder 1. So everybody agree? Excellent. So I'd say that's the right answer. Okay, now I want us to do this one. Okay, I want us to do 501 divided by 100. And I want us to do it the same way. I want us to write our answer with the remainder system. Okay, so students will do this. into 501, and they'll say 5, remainder 1. And I'll say, yes, you got the answer right. 501 divided by 100 is 5, remainder 1, written in the R period system. And then I'll say, well, let's look at this. 11 divided by 2 is 5 R period 1. 501 divided by 100 is 5 R period 1. Okay, so is this correct? Is 11 halves the same as 500 divided by 501 divided by 100?
Yes.
I mean, R period 1, R period 1, yeah, it looks the same. It's the same. But okay, so what is 11 divided by 2? What does that mean? If we said 5 remainder 1, what does that mean? Well, at least in our school, we also teach the fractional way. Yes, 5.5, right? Is this 5.5? No, it is 5 and 1/100. Okay, very, very different numbers. Now, what does the R period system, what does the remainder system do for us? Well, it lets us know how many are left over. That's lovely. It's true. Okay, it does. However, writing numbers as mixed numbers does the same thing. Okay? Here is how many are left over in each case. But writing it as a mixed number also tells us out of how many. And that out of how many makes a big difference. You can graph on a number line 5 and 1/2. You can plot it on the number line. You can plot 5 and 1/100th on the number line. You cannot plot 5 R period 1 on the number line because you don't know where it's going to go. It'll go between 5 and 6, but that's all you can tell me. Okay, because you need to know those denominators, not just the numerator. Okay, another reason to teach the algorithm, this is why, by the way, I don't use the R period system. I tell my students, I get up on my soapbox, I just do that. I said, I'm on my soapbox. I hate the R period system. I don't like the remainder system, okay? Because it doesn't express enough meaningful information. It doesn't give the students the full story. Also, when you get into algebra, if students understand and are kind of well equipped with this algorithm of doing it as a fraction, they then can use that algorithm that they've been using to divide polynomials. So x goes into x squared, x times, and I'm just gonna, you don't have to worry about this, those of you who don't teach algebra, but you multiply through. And then when we subtract, we get negative 3x minus 5. And x goes into negative 3x and negative 3 times, and you multiply that one through and subtract, and you get remainder 1. It's the same remainder 1. We do long division. Don't tell your students that once you like go into calculators, you never have to do long division again. It's not true, okay? We do long division in algebra. But here, because instead of it separating by place system, we have it separated by terms. We put a plus sign because this is positive. Yes. And notice, just like over here with the fraction, the remainder goes in the numerator and the divisor goes into the denominator. So if they learn that algorithm early, and that they're not only talking better about actual numbers and building their number sense, they're also learning an algorithm that's going to help them later on in algebra. Okay, let's talk about exponentiation next. All right, what is multiplying? That's a review question. What is multiplying? Fast adding. So what's exponentiation? Fast multiplying. Excellent. Okay, so number talk on exponentiation. Another Lutheran question. What does this mean? What does x to the 4th mean? X times x times x times x. Excellent. Fast multiplying, okay? And x to the 3rd. X times x times x. And then I would literally ask my students, what happened to the x? Where did it go? Where'd it go? Just disappeared. What happened? How did we get rid of it? Division. Yes. Now, what do most of my students say at first? Subtraction. They'll say subtraction. I'll be, well, let's go the other way. If we say x times x times x, and we have x cubed, and then we go to x to the 4th, and what is exponentiation again? It's fast multiplying. So if we go this direction, we're multiplying by another x. So when we go the other direction, how do we get rid of it? We're dividing. Yes. Okay, so then I tell them, don't just say x times x because I know it's fast multiplying. Use what we just talked about. Divide by x. That's going to make one of these cancel out, go away. That's why it's x times x, yes? Okay. This one, x. Okay, and by the way, my next topic is invisible numbers. There's a 1 there, right? We keep going down by 1. We divide by x. That's why we get 1. So what is x to the 0?
1.
What's it? Yeah, x over x, which is 1. Very good, okay? This also can help students understand. We have to memorize it, but this is why. This is why it works. And then it keeps going. Okay, negative exponents do not produce negative numbers.
No.
Again, we're following the same rule. We divide by x. So what's 1 divided by x? 1 over x, okay? X to the negative 2, 1 over x times x, so 1 over x squared, and so forth. Okay, so students can see with these talks about why, the things that we're having them memorize, why they work the way they do. All right, invisible math. We just talked about a couple examples. We had one here. We actually have one I didn't even write up. You can also see the 1 show up this way. There's an invisible number right there. X times x times x times x times 1. There's a 1 there. There's a 1 there. There's a 1 there. There's a 1 there. And then when we divide by x, left with 1. Likewise, when we divide by x, let's just say we take x to the negative 3. Okay, and we didn't do this whole chart. We'll just say x to the negative 5. Okay. And if you're asking students to write that without a negative exponent, well, they know they have to move the power down to the denominator, and then a 1 shows up. So talking about where we don't have numbers and then they show up is really helpful. Here's one with, again, distribution. What are we distributing? And students will say a negative sign. I'm like, a negative what? We don't, what number are we distributing? We distribute numbers. We don't, yeah, because it's negative 1 that we're distributing. Okay. All right, let's do some multiplication methods throughout the world. For all of these problems, I'm going to do 54 times 36. All right, the first method is the Chinese grid method. Chinese grid method, you draw boxes. In this case, it looks very much like a Punnett square. We're going to put the top number on the top and the bottom number on the side. And for the Chinese grid method, we divide the squares into diagonals. We then multiply each number by each number. If it's a 2-digit number, you put 1 on one side and 1 on the other. So we get 15 here, 12, 30, and 24. And then you simply add the numbers that are in each diagonal row. So 4, 4, 9, and 1. Our answer to the problem is 1944. I'm going to leave that up. And rather than explain what's going on in the algorithm, I'm going to show you some other methods so that you can start to see these numbers, these same numbers kind of appearing in all the algorithms so you can see what's going on. The next one's my least favorite to show. Don't judge my straight lines. The Japanese grid method, or the Japanese method, we draw lines. So we're going to draw 5 lines, a space, and then 4 lines. I'm going to switch markers. And then for the other, so that's 54. For the other number, we're going to draw 3 lines, which cross it, a space, and then 6 lines. All right, is everybody able to see the black lines, even though it's kind of more gray at this point? Okay. The method then has us kind of isolating the first part of the number and the last part of the number. We'll talk about what those are later in a different method. And then counting the number of times these lines intersect. So using multiplication to help us add quickly, okay, fast adding, it's 3 times 1, 2, 3, 4, 5. So we get 15 over here. 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5 is 30 here. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 4 times 6 is 24. 1, 2, 3, 1, 2, 3, 4, we get 12. Notice 15, 24, 30, and 12 are the exact 4 numbers that you can see in the Chinese grid, Chinese box model. Yes? Okay, and so the Japanese then take this first number they isolated and the last number they isolated, and they write it together as one number. Again, we'll look at another method shortly here that'll show you why this works. And then for the 30 and the 12, they add it together and they place the numbers kind of in the middle. And again, we get the answer 1944. All right, let's talk about the ancient India model. This one will probably connect all of the dots for you. Okay? So we have 54 times 36. The ancient India model says we're going to multiply these numbers and these numbers, kind of the extremes of the numbers. 5 times 3 is 15, and 6 times 4 is 24. We're then going to multiply the numbers in the middle and then add them together. So you have 30 plus 12, which is 42. And so now you can see that this identically matches the Japanese model, but you can see where those numbers came from. Right? We did, the 15 came from multiplying 5 times 3, right. The 24 from 6 times 4, and the 42 in the middle from this one times this one. And then adding them together.
Which one?
Oh, sorry, 30,
5 times 6.
30, 12, 30 plus 12 is 42, and then 1940. All right, the next model method I want to call either the FOIL with base 10 method or the Erika Mildred method. Actually, I should just call it the Erika method. I came up with this method when I was in 5th grade. And I just thought I found the coolest number trick ever that allowed me to not show my work on my paper, which I thought was great because I didn't have to use up all of the lines of paper that all my classmates were having used. So with this one, and this one is very similar to this ancient India one, which I didn't know, okay? I multiplied the way I was taught. I did 6 times 4, which is 24, and I carried the 2. Then I did 6 times 5 is 30, plus 2 is 32, but I didn't write down 32. Instead, I kept 32 in my head, and then I multiplied 3 times 4, which is 12. Well, 30 plus 12 is 42, so I wrote down the 2 and carried the 4, right? We always write down the ones digit and carry the next digit. And then 3 times 5 is 15, plus 4 is, oh goodness, I didn't add that right, hold on. At 32, 44. Yeah, I said 44, I just need to 44. And then 19. All right, what I didn't realize at the time is that I was doing is recognizing that a ones digit times a tens digit and a tens digit times a ones digit are always going to add together. Right? Because they're always going to be in the value of that tens column. All right, this also can apply to FOIL. Okay, obviously that's base 10, because if you have, just picking easy numbers for now. Okay, we do the first in FOIL, x times 2x, which is 2x squared. Okay, notice the binomial, they're in the same order of degree, and degree of 1 and then a constant degree. But the O and the I are going to combine, just like the tens and the ones are going to combine. So this is 4x and this is 6x, so it should just be 12x, and you don't have to do the O and the I and then write them together. And then 3 times 4 is 12. Now, if we have time, which I keep looking at my clock and I don't think we're going to, but if we have time or if you just want to pick my brain later, I can show you how this method works with larger numbers and also with larger polynomials so that you can write your entire answer and combine like terms as you go. Okay, the last method I want to show you on multiplication methods throughout the world is the Egyptian method. This one, you write the numbers across from each other, 54 times 36. Underneath the 54, we're going to start with the number 1, and we're going to double it. 2, 4, 8, 16, 32. We keep doubling until the next doubled number would be larger than your top number, so you wouldn't write 64 because it's too big. We'll then start over here with 36, and we're also going to double. If you show your students this as a number talk, I would have them use a calculator because you don't want to waste the time kind of doing it by hand and doubling the numbers. Whoops, I set down the wrong one. So for this one, the doubled numbers are 72, 144, 288, 576, and then 1152. Okay. The way this method works, and again, this is a great one to have your students try, like show them this and then ask them to go home for either homework or extra credit and try to figure out why, okay, is you circle the numbers that add to 54. In this case, it's going to be, I wrote that on my, I should have circled those. It's going to be 32, 16, 4, and 2. Those add up to be 54. Right. You're going to then add the numbers to the right, 72, 144. Again, all on calculator is fine. 576 and 1152. This adds up to 1944. Now, I'm not going to leave, don't show your students this one, but I'm going to give you an easy problem so you can see what's going on, okay? I'm going to do 13 times 7. Okay, so you show your students this one. Here's how it works, okay? We're going to start with 1, then 2, then 4, then 8, then 16, then 32. Oh, sorry, not 32, and not 16. Sorry, I went too far, okay? And then over here, we're going to do 7, then 14, then 28, then 56. Adding the groups that add to 13, we have 8, 4, and 1.
Right.
So we have 8 groups of 13, right? 8 of the 13, right? 8 groups times 7. 8 groups of 7 is 56. 4 more groups of 7 is 28. And then the final group of 7 is 7. So we have 8, 12, 13 groups of 7 broken out there. Does everybody see that? Okay, so that's why it works. That's how it works. It always works. Okay, so have your students kind of ponder the harder one. Unless you have really younger ones, and maybe give them 13 times 7 when you're working on your 13s. All right, next. Whew. Factors and primes. I want to talk about something I call hockey stick math. So prime numbers are natural numbers whose only factors are 1 and itself. So we have 2, then 3, then 5, 7, 11, 13, 17, and it continues on. If you can get your students to write a number as the product of prime numbers, it actually allows us to do a lot of things with that. We can reduce fractions, find the GCF, find the LCM, find common denominators, and find factors needed to split the middle term in algebra. A way that I have students learn to get very comfortable with primes is what I call the hockey stick method. So let's take the number 480. To factor this, instead of like the factor tree model where you just kind of randomly pick 2 factors that, like 48 and 10 or whatever you pick, you always start with the smallest prime number and you keep using it until you can't use it anymore. So we have 2 there, we have 2 there, we have 2 there, 2 times 60, then 2 times 30, and 2 times 15, and only here do we stop using 2. And then we check to see if we can use the next prime factor, which is 3, and we can. And we stop when we get to another prime. So one of the nice things about the hockey stick method is that it tells students when to stop, and it also organizes their numbers. So 2 times 2 times 2 times 2 times 2 times 3 times 5 is 480. Or 2 to the 5th times 3 times 5 is 480. You can also use this to help students then find other factors. For example, let's see, 32 times 15 is 480. 16 times 30 is 480, and so forth. Perfect squares and simplified radical form are also very helpful. Having your students memorize the perfect squares, I would say up to 16 squared, 256 would be really good. But let's say we have a problem like this. Again, this is for kind of middle school, older students. You have 100 squared to 192, and you want to write it in simplified radical form. So you'll start with the largest perfect square that is a factor of 192. Again, you have your students use a calculator, okay? Don't have them doing the number crunching on the side. Have them kind of come up with it. So 169 isn't a factor. 144 isn't a factor. 121 isn't a factor. You keep working down. Turns out that 64 times 3, when they're doing it on their calculator, if they know their perfect squares, 64 times 3 is 192. So square root of both parts, you would have 8 square root 3. All right. In our last 5 minutes, I'm at number patterns. I've already talked about powers. Powers are very helpful. We can use them here. You saw 2 to the 5th. Frankly, over here with this method, these are actually the powers of 2, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, okay? Another place where you can see powers come up is in Pascal's triangle. So I kind of want to end today with Pascal's triangle. On the back side, you have filled in Pascal's triangle, okay? It has kind of a diagonal row of 1s on each side of it. And then once we kind of get into the triangle, the 2 numbers above any hex adds to be the number kind of below and right in the middle of that hex. And that's how it's all filled in. But there are many patterns in Pascal's triangle. I'm going to just introduce some of my favorites. So the first one is the sum of a row. So if you take this first row, it's 1, and then 2, 4, 8, 16, 32, 64, 128, 256. It is the powers of 2. Okay, so the sum of any row of Pascal's triangle is a power of 2. Also, the numbers in each row are the coefficients when we expand a binomial raised to a power. So, for example, I need some room. I'll do it right here. A plus b to the 6th. Okay, you go to the row for Pascal that has the 6 in it. It's going to be 1a to the 6th plus 6a to the 5th b plus 15a to the 4th b squared plus 20 a cubed b cubed plus back to 15 a squared b to the 4th plus 6 a b to the 5th plus 1 b to the 6th. And we don't need to really worry about the other part with the exponents and the variables but the coefficients come from Pascal's triangle. Next, suppose you wanted to, this is a topic in probability, it's called combinatorics. Suppose you wanted to know how many round robin matches there could be in a tennis tournament with 13 contestants. That can actually be answered with Pascal's triangle. So, basically what we're asking, if it's a singles tournament, right, is that we're going to have groups of 2, and it's like how many groups of 2 can we make out of all those 13 so everybody plays each other once. So we go down to the row that has 13 in Pascal's triangle, okay, and there's one way to create a group of 0 players. There's only one. Okay? There are 13 ways to create a group of just 1 player on the tennis court. But if you have 2 players on the tennis court, there are 78 ways. So that tournament would take 78 matches to get everybody to play everybody else one time. Next one, the sum of a diagonal. So if you take this and we go across and we say, like, for example, the diagonal 1 plus 3 plus 6, the sum of it is down and to the right, almost like a mini hockey stick. It's 10. That works in both directions. You just have to go down to the left if you go the other direction. Okay, so that's the sum of a diagonal. The next examples relate to figurate numbers. I have figurate numbers on the bottom of your handout. Figurate numbers are numbers of arrangements of dots as geometric figures. So the triangular numbers are 1, 3, 6, 10, because every time we add another row of dots, that's how many dots we have all together. The figurate numbers for triangular numbers are right here, 1, 3, 6, 10, 15, 21, 28. Again, they go in both directions on Pascal's triangle. The square numbers, those are our perfect squares, 1, 4, 9, 16, 25. Those are in the same diagonal row as the triangular numbers. You just have to add 2 hexes together. So 1 plus 3 is 4, and 3 plus 6 is 9, and 3 plus 6 is 9, and 6 plus 10 is 16, then 25, then 36, and so forth. This, the tetrahedral numbers. Those are 1, 4, 10, 20. Those are just a diagonal row. You can find it. The square pyramid numbers are 1, 5, 14, 13. It's the same tetrahedral diagonal row, just add 2 hexes together. The last one I want to show you before some pictures, and I know I'm right at 3 o'clock, I promise I'm almost done, is the Fibonacci sequence. The Fibonacci sequence is in Pascal's triangle. First of all, the Fibonacci sequence is started by 2 1s And then you take the two preceding numbers to add to get to the next number. So then 2, 3, 5, 8, 13, 21, 34, and so forth. So this one's a little harder to see, but if you go to the vertex and kind of go across diagonally, but from a vertex, you will get Pascal's triangle. So this one is 1. Then the next vertex is actually in between these first two ones right here. You still just get 1. Then you get 2, then 3, then 5, then 8, and so forth. So if you couldn't see that as I'm kind of trying to show it up here, I'm happy to show you after the presentation. To end, and of course, I didn't think I would have time for all of those advanced higher level math examples, but I'd be happy to talk with you about this later. But I just wanted to show you, for those of you who have younger students, you can still work with them in Pascal's triangle as you are having them memorize their multiples. Here are the multiples of 2. You can have them color. Please don't make high schoolers color. Okay? They don't like the color. But the little ones love to color. Here are the patterns of multiples of 3. Multiples of 4. Multiples of 5. Multiples of 6. Multiples of 7. Yep, 7 works too. Multiples of 8. Multiples of 9. Multiples of 10. Okay, God's world is an orderly world. His numbers are orderly. And it is the language in which he has created a wonderful, marvelous universe. I hope you enjoyed this talk on building number sense in our students. And if you have any questions, I'm here most of the time. So, thank you. Yes. You're not done. You're not. Is that right? So short. All right, let's go back. Sorry. Okay, so now we get to talk about higher level math. Maybe I did that on purpose. All right, so let's talk about mid-segment theorem with Pythagorean triples. And actually, what I'm going to do is I'll cover a couple of these, and then I want to get to like your questions.
Okay.
All right, so the mid-segment theorem is actually one of my favorite theorems in geometry. It says that for any triangle, if you connect the midpoints, you create smaller triangles that are exactly half of the size in terms of its side lengths as the larger, and always created sides that are parallel to that third side. So let me show you what I mean first. And what I want to do is I want to connect, because you can do this for any triangle, but I want to take a right triangle. Okay, so this is a right triangle. And I'm just eyeballing it right now. Having students do this on graph paper is a much better way to do this, because then you can tell them how many spaces across, at least for the first two, and they can even kind of use the grid to help them with finding the midpoint in the third one. Okay, so as they connect it, this one right here will be parallel to this side, and I'm just going to come a little bit higher with this one. This one right here will be parallel to this side, and then this one right here will be parallel to this side. We also get another right triangle. Okay. And then I'm going to do one more, and then I'm going to show you how I connect this to Pythagorean triples. Okay. So the mid-segment theorem says, let's just say we call this length of 3, and this a length of 4, and this a length of 5. The mid-segment theorem says that not only is this side parallel to this side, but it's twice the length. Right. So this is going to be 6. This length of 4 here is twice the length. It's going to be an 8. This length of 5 here is twice the length. It's going to be a 10. Now, For those of you who teach Pythagorean theorem, teach the triples also, right? We haven't memorized the most famous triple is the 3, 4, 5. But then the multiples of this are also triples. The 6, 8, 10 is a triple. Now watch what happens again. We got 6, so this side is 12. 8, this side is 16. 10, this side is 20. Also a Pythagorean triple. So all the triples are triples. It's easier to have students construct these largest to smallest. So if you wanted to do more than that, have them draw an even larger triangle first and then do it 4 times. Still start with the 3, 4, 5 in the middle,
Right.
and then go out from there. Okay, quickly finding M and B in standard form. When you transform, how many of you are teaching algebra? Okay, good. No, thought maybe a fifth of you. That's good. So AX plus BY equals C into slope-intercept form, into y equals mx plus c. We did it with numbers before. Sometimes have your students do it with all variables. And have them watch what happens. Because students can actually, I know when we do graphing, we do standard graphing, we can do the kind of intercept graphing to do quick graphing. But you can also have students notice when you're given something in standard form, how to quickly spot the M and the B, the slope and the y-intercept. So notice when we get this into y equals mx plus b form, the ax moves to the other side. And then we divide both sides by b. Yes?
Yes.
So your slope is always a negative a over b. And your y-intercept is always c over b. And you can just have the students kind of remember that, and then they can do it right here without having to transform first. The next thing, xy relationships, zeros, factoring, and TI connections. We use the TI. I like it better than Desmos. I think Desmos helps them too much. I also like it better than Desmos because computers are bulky. And this is a lot easier to carry around. Okay. I also like it better because it makes them work harder to do things. And if I do want them to graph it on their own, they literally have to draw out what they see. They can't just take a screenshot or just print out whatever they did on Desmos. I'm not saying Desmos is bad. I like this better. What I like to do is help students understand the relationship between a graph, a table, and an equation, and let them see how those three go hand in hand. When you get into algebra, you help students understand that when it crosses, we'll just start with the quadratic. The two places it crosses the x-axis are the solutions because we always want y to be 0, and y is 0 there. This is why on our TI they are called zeros, okay? And we call them zeros to the equation. So if, for example, this was at -3 and this was at, let's just say 4, then the solutions are x equals -3 and x equals 4. What are the factors? Well, the factors, according to factor theorem, are just the opposite signs. So helping them see the connections between the zeros, the solutions, and the factors, okay, of the equation are really helpful. I like to help my students, same with talking about quadratics, okay? If it just crosses it once, if you solve it, you're going to get x equals 3 or x equals 3. When you get the same solution that tells you you have a vertex going on, okay? So then that means that x minus 3 squared equals y, or equals, because we know y is 0, is the equation for this parabola. So helping them work between tables, graphs, equations, really good things to do and having them see that on the TI. And again, those of you who aren't teaching algebra, that's okay. But it's all of the stuff we're doing, this is all kind of where it's leading to, and then even farther, right? When we get into pre-calc and calculus and trig and all that. Okay, next one. This was a really cool article that I read by a professor who's, I think, out in Colorado, completing the square and parabolic transformations. Completing the square transforms, oh no, we are at 3:10. I'm going to pause on that. I will be happy to talk to you guys, anybody who wants to talk about any of these other things, but for the last 5 minutes, let me turn it over to you guys. What comments, thoughts? things that you guys have, things that you've experienced in your classroom about building number sense. Yes?
When I have K1, 2, so you know where now. And when I introduce the numbers, I start with base 10, 0 through 9. And at that time, I also introduce them to base 3 so they can see what we're doing. And then we have another one where we add one, so it's, I can't remember what we call it, ziggle. So is that wise? I mean, they've been doing well with it.
Sure,
and-
I mean, base 2 and base 3 are definitely ones that I think if students got more exposure early, it wouldn't be as hard later on.
Right, and they do catch it.
Right, and we do use, like in Sierpinski's triangle, we actually have base 2 all over the place. In Pascal's triangle, we do also. So yeah, I mean, I think that, I don't think that there's anything wrong with having them count in different systems.
Right, because it really helps on the number line too.
Right,
Because you have
absolutely.
0, 1.
And it lets them know in our base 10 system, that's what we're doing. We basically are counting 9 and then rolling over one place.
Okay.
Good, yeah.
When you show the different multiplication methods, do you let them use them in your homework when you want them?
So full disclosure, if I taught younger, absolutely I would. Because they're all algorithms. We have to understand that, I'm not trying to say that this is like I'm an advocate of new math or anything like that, okay? But I am understanding that our algorithm that we learned isn't necessarily a better algorithm, nor is it a worse algorithm, it's just an algorithm. So I would say yes, and I would say if I were teaching younger students, I would probably after number talks and after some practice, I would give them some where you make them do it all the different ways and then you let them pick their favorite, right? Because they're always gonna have ones that like, this one really resonates with me. Eventually, when they get to me, man, if they don't know their multiplication tables, if they don't know how to multiply and divide and add and subtract, they're gonna be really struggling because we're doing this stuff. So I think anything you can do to build their number sense is great. I tried to show my 5th grade teacher, and my 5th grade teacher said something to me like, that's nice, but I can't see your work, so you need to do it the way I showed you in class. So I would advise not saying that to students, right? I would advise them, I mean, again, you do have to grade something, but all of these methods, there's work to be done, right? There's a process by which we're doing things. So yeah, I think, yeah, have them use multiple ways. We do that in algebra, right? We solve quadratic equations by factoring, by completing the square, by quadratic formula, by graphing. We have multiple ways to solve. So yes, get them used to that early. I think that's good. Yes?
I just throw out the idea that when I taught exponentiation, I didn't let kids say x to the fourth. I made them say 4 factors of x.
Okay, I like that. Yes, 4 factors of this. Yes, that's a word, factor, that kids don't know. I mean, you can ask them to factor and you can, have them do a factor tree and then you say, okay, what are factors?
Yes.
And then they look at you like, I don't know. So connecting between, they're great at learning the algorithms. Our kids are great at memorizing and we make them memorize, so they're good at algorithms. We gotta make sure they understand what it is they're memorizing and why it is, and the language of mathematics. Yes?
I think too, teaching what the operation or the law is that went with it. I've given this example in another talk, but I learned about the identity law and dividing fractions. I only knew number, don't be shy, flip yourself and multiply. Literally, that's what I knew.
Right.
No one ever told me it was identity law. I went to engineering school and learned that at a homeschool event.
Yes. Well,
That I
flipping
was
is actually, I think, inverse, but
Sure.
you're absolutely
But
right.
that was what the ditty was.
Right.
In like
Right.
3rd grade.
Yes.
No understand.
And I
Yes.
didn't understand that I was using the identity law
Right.
until I was in my 30s.
Right.
And I studied engineering. So give them the why.
Yes, correct, absolutely. And this is not saying the ditty's bad,
No.
right? It's good, and we do dividing by a fraction is the same as multiplying by a reciprocal. And
Right.
my kids are they get so I don't think they get tired of it, but they're still smiling. But I like divide. I'll say the sign in front of the term, and then the x goes with the term, and so it's good. It's good to have the things that stick up there for the algorithm, but yeah, definitely teach them the why. Definitely. Okay, you've been a great audience twice. Thank you.